Okay, guys, so in 13.5, we're going to be learning some new parent function graphs. Just like we have other parent functions, like the quadratic is this parabola shape, and the absolute value is this v shape, we want to know the shape of the sine, cosine, and tangent graphs as well. So, what I have here on the left, we're going to focus on what I have sort of highlighted in green. What we have down this first column, all of these angle measures in degrees, they should look really familiar to you. Those are the special angles. We talked a lot about those in 13.3. Okay, and for instance, if I take 0 degrees and I plug it in for theta right here, sine of 0 is 0. If I take 30 degrees and plug it in, sine of 30 degrees line on that unit circle. And you can see that they, give you the values for all of them. And essentially what they did is they said, okay, we're going to treat theta as our independent variable, meaning it's going to go on the x-axis. And then we're going to say that sine of theta, that's going to be our dependent variable. So they plotted all of these numbers as y values on this graph over here. And there's some of those that I have highlighted, and you'll kind of see later in the week why that is. But for example, we're going to have the point 0, 0 right there on our sine graph. Okay, we're going to have the point 90, 1. It's right there. We're going to have the point 180, 0. It's right there. We're going to have the point 270, 1, negative 1, right there. And 360, 0. And that's right there. And they have a bunch of other points there as well. It's coming from all of these in-between spots as well. But you can see it makes this really cool graph. It kind of looks like a wave, right? And they just drew what we call one cycle of the graph. But really, we know we can keep going around and around the circle. We can go 360 degrees. We can go around again to 720, 1080. So this graph, while they only drew one cycle, I want you guys to know it does keep going. I'm going to draw a little arrow there at the end and at this end, because we could also go around in the negative direction, okay, and produce this graph as well. So this is a graph that you're going to want to be familiar with, and we're going to practice drawing it a lot, so don't panic yet. Now, I also want you to be familiar with cosine. And what's happening here is our independent variable, if we go back over to this column, our independent variable is still theta, but now we're going to plug theta, for example, 0 degrees. We're going to figure out, okay, cosine of 0 degrees, oh, that's 1. Oh, cosine of 90 degrees is 0. So we're going to start to plot some of these points for cosine. Okay, and that's, you can ignore this little point right there. I don't know why I highlighted that, but these points right here are coming from the x-coordinates on this unit circle. Okay, if I plot those points, the x-coordinate here at 0 degrees is 1, the x-coordinate at 90 is 0, the x-coordinate at 180 is negative 1. You start to get the idea. Again though, this cosine graph makes that nice wave shape, but I also want you to understand it does, this wave shape does continue on. So I'm going to add in those little arrows. All right. Now, sine and cosine, yes, they're trig functions. Yes, we want to know these graphs, but they fall under this umbrella of being called a periodic function. And basically, a periodic function is a function that repeats itself after a particular distance. if you keep going around and around this circle, you're going to repeat yourself. Those x coordinates are going to repeat themselves. So it makes sense that this is a periodic function. Lots of stuff out there in the real world, repeats itself. The seasons, hours of daylight, temperature. All of those can be modeled with these periodic functions. So they're super important. Okay, so there's some characteristics that I need you to be able to discuss with these functions. So let's turn the page here. So cosine and sine, one of their special characteristics that we want to talk about is what's called the period. The period is how long it takes for that graph to repeat itself. More specifically, it is the horizontal distance needed to complete one cycle, aka how long until we repeat. Oh, you can't see everything, huh? Okay, there we go. Better. So cosine and sine is parent functions, and you're going to see how this changes, in a couple days here. But as parent functions, they have a period of 360 degrees. Okay, now we will be transforming them later. We'll look at some equations where they're transformed right now, and we'll see how that might change. So, if we have a situation where there is a horizontal compression or stretch, that means if you imagine a slinky, okay, I wish I had one right now, but I don't. If you had a slinky, imagine pulling that slinky apart. You'd be stretching it horizontally. Or if you had a stretched out one and you pushed it together, that would be a horizontal compression. The thing with horizontal stuff, and you'll remember this from previously this year, it's always on the inside, and it's always opposite in operation. So I have two examples that I've added in here. If we look at this first example, y equals cosine of 2 theta. It's not just cosine of theta, it's cosine of 2 times that angle measurement. Notice that 2, it's on the inside of cosine. If it's on the inside, it's horizontal. If we are changing this horizontally, we are going to be changing the period of that graph. The period used to be 360. To figure out the period of this graph, if we're multiplying on the inside, what we're going to do, I shouldn't have drawn that, let's get rid of that little dot, we're going to take the period and divide it by 2. Which means that this graph, and you'll see tomorrow on an actual graph, that it will complete a full cycle by 180 degrees. Again, if we look at this example that I added in here, it's not sine of theta, it's sine of 1/2 theta. Again, that 1/2, it's on the inside. Inside stuff is horizontal, and it's multiplying theta. So, to calculate the new period, we're going to take 360 and divide by 1/2. That the opposite of multiplication is division. If I'm dividing by a fraction, I flip and multiply, and that means the period is now 720 degrees. So, just to recap that really quickly here, if we go back and we look at those graphs, which I have to find a piece of paper here. If you look at sine, it takes from 0 to 360 to complete a full cycle. If we start multiplying the inside of the trig function, if we start changing theta in there, that will change how long it takes to complete a full cycle. Okay. So that's one thing that might be affected. Another thing that might be affected is something called the amplitude. You've probably heard that word before. Amplitude is defined to be half the vertical distance. Half the vertical distance between the max and min of the graph. So if we look at those two parent functions again, if I look at the graph of, let's say, sine, here's the maximum, here's the minimum. Now, the vertical distance between the two. All right, this is a distance of 1, and that's another distance of 1, so that's a total distance from the top to the very bottom, a total vertical distance of 2. The amplitude is defined to be half of that. Okay, now that means on our parent function, we start out with an amplitude of 1, but if I start changing the equation a little bit, notice where this 3 is. This 3 is not by the theta, it's on the outside. Anytime we're multiplying cosine or sine on the outside, the amplitude changes. It's really easy to find. You just take the absolute value of that number in front. The absolute value of 3 is 3. Over here, the number in front is negative 4. Absolute value of negative 4 is 4. So to sort of summarize what's happening here, and you're going to see the graphical changes tomorrow, but to summarize what's happening here, if we have a vertical stretch or compression, okay, so that's something on the outside. I'm just going to write something very generically here. So I'm using sine, but this could be a cosine as well. This will be some number b, and this will be some number a. To calculate the amplitude, we take just the absolute value of b. So this b, that's our vertical stretch or compression. Let me get a different color here. Our horizontal stretch or compression, horizontal stuff is on the inside, deals with this value that's multiplying theta. If I ask you to calculate the period of this graph, aka how long does it take to complete a full cycle, you would take 360 and divide by, it's technically the absolute value of a, a lot of times it'll be positive, and that will get you the period of the graph. So, what I have down here are 6 equations. I want you to pause the video and try to identify the period and the amplitude of each. And then when you think you have them, go ahead, play the video again, and see how you did. So go ahead, pause the video at this time. Okay, so now that you're playing the video again, let's see how you did. So number 1, the amplitude is 2. The period's going to stay 360 because there's no number in front of theta. Amplitude on number 2 is 1/3. Period's 180 because 360 divided by that 2 is 180. Number 3, you got 0.7 as your amplitude. The period is 720. This one's tough. Number 4, when you take 360 and you divide by 5/3, you're really multiplying by 3/5. That does simplify to 216. And the other maybe tricky thing, like number 5, make sure you said the amplitude was a positive 2. Number 6, make sure you say the amplitude is a positive 1. Amplitude is a distance. So is period, really. Amplitude is a vertical distance. Period is a horizontal distance. All distances are positive. Okay, so this completes part 1 of the video that you have to watch today.